Yes, good afternoon. So I'm Erwin Haan. I'm from the Accelerated Big Data Systems group at TU Delft in the Netherlands. And today I want to talk to you about enabling SQL to FPGA using HLS for filtering and stream transformations. And so FPGAs have really been on the rise in HPC and big data lately, and they're very good at doing complex parallel problems. Due to their nature, they can have very deep pipelines for data flows and processing. And most of the issues stem from data movement. And so the goal of the group is to provide high throughput, low cost big data solutions. And so a little bit of an overview of what I want to talk to you about today. So I want to give a little bit of context on why I did what I did. And then I want to give a very brief sort of point to what Fletcher and Arrow are and what they do, and a couple of usage scenarios, and after that I want to talk more about sort of the architecture, implementation, and how we tested these. And we'll end with a little bit of an outlook. So for the context, so the main thing here is that I want to generate essentially a filter. So in the group we have someone, Lars van Leeuwen, he worked on a Parquet file reader for FPGA, and then a decompressor to decompress the data from that Parquet file. And so the thing is, before it touches memory or even the CPU, it would be great to be able to apply some very small transformations and filters. And so the idea of this project is to automate as much as possible of that filter generation. So traditional FPGA development workflows they're complicated hardware designs. You need to write, HDL. Obviously, this gives you high performance and complete control over whatever your filter or kernel is going to do. But the fact that it's complicated means it's expensive. And so on the other side, you have the high-level synthesis, which you have moderate performance, and depending on what you can do, you can absolutely reach the same speeds as some of the HDL implementations. It's easier to do, so it might actually save you time and money if it can reach sufficient throughput. And so earlier today, Haan, who's over there, gave a talk on the Fletcher framework, which one of its aims is to always saturate system bandwidth while reading and writing to arrow buffers. And so that's a standardized memory layout, and that is obviously great for interoperability and data sharing. So a really quick overview of what the arrow in memory format is. So a traditional memory buffer will have, for example, in C, structs will be, together, all of them. And then for arrow, what it does is it will split them up into separate buffers for each and every column, essentially, in the record batch, which is like a table, essentially, for arrow, which has a certain specification, which is a schema, and it says, okay, this field is an integer, it's this large, and so on. And so the idea was to make a compiler that takes an SQL query and a schema, and the schema is essentially like the SQL table definition in this case, and generate hardware that will execute that query in a streaming fashion from the Fletcher streams that are specified by the schema. So it's written in Python, and so it builds on top of Fletcher, it builds on top of HLS tools. And what it tries to solve is sort of, you have on the left here, there's a couple of kernels or other sources that generate streams of Fletcher compatible, Fletcher compatible streams with a lot of data. And if you have a small filter action you might want to do before you pass it on to the next Fletcher compatible kernel, and you want to do this automatically. So if you want to generate dynamic filters, right now the easiest way to do it is to just have the CPU do the actual filtering, and so you get a full round trip essentially to the CPU for the data. And more ideal is to automatically generate that middle core. Right now you can obviously do this. You can just write the HDL yourself. You can write the HLS yourself, and then you have your fixed filter. But if your filter changes, this means you need to redo your design essentially. And so the goal of this project was to fully automate that whole internal filter. So if you have two kernels, one on the left, one on the right, that are larger fixed function kernels, but in between there's a little transformation that you might need to do and that might change. For example, there's a date filter or some other thing that might change through time. Then it would be very nice if we could automatically generate these. And this obviously means that the bulk of the data now bypasses memory, and so you don't have any round trip time. You don't need to push it over the host interface towards the CPU, for example, for processing. And then here is a little bit of a detail. So for this core, what will happen is that the input and the output streams on the left and right, they're essentially only dependent on the schemas you deliver. So they can be 1, they can be 5, 10, and so on. So that's, you can do essentially as many as you like and your hardware allows. So for the implementation part here, is Fletcher for data movement. This is obviously, it means that especially when using CAPI and for example the Snap framework, you don't actually have to copy the data over to the FPGA or vice versa, because the FPGA can directly access your host memory over the CAPI interface. And Fletcher makes this even easier, because this means that anything on the host or other accelerators can also write to that same buffer if you want. So this greatly simplifies the design of this sort of automated system. Then for the parsing front end of this compiler, so it didn't make much sense to write our own. So we used the Mozilla SQL parser. And then for the final code generation, so there's a project, and what it does, it takes any input and it can transpile it to any output. This works for Fortran, C++, and Python, and it uses Python ASTs internally. So we use the unparser, which takes a Python AST that you can generate, and it makes C++. And then you can feed that C++ into a tool like Vivado HLS, and this can create your kernel, and then you can run your normal FPGA tools to get it where it needs to go on an FPGA. And so internally, the tool also produces a Python 3 AST. And so this is an architecture overview of the compiler. So it has a front end which generates a custom AST. It passes it off to the middleware, where it goes through a couple of very standard compiler transforms. It does some simple constant propagation. It does some desugaring and some normalizing of the parsed AST. And then finally, there's some more Fletcher and output specific transformations. This generates the final Python AST, passes it to the backend, and then the backend generates the readable HLS C++ code essentially, which can then go on and you can compile it into HDL. And this is built on top of several little things here at the bottom, the dependencies and such. And I want to just go through a couple of these just to highlight certain parts. So I want to start with the front end. So originally the front end, they output essentially what you see here on the right. It's essentially a JSON type format. Now, for doing transformations on this and for writing a compiler based on this, it's not very useful. It makes transformations much harder than they are needed to be. Now, thankfully, it's a fully open source parser and it's based on pipe parsing, which makes it relatively easy to extend. So after a bit of work, it can actually output full AppSec syntax trees. So all the little parts near the top for the query, they map to the different parts as colored on the right here. And these are classes that are based on the Python AST classes. This means all the tools that work on Python ASTs for walking the AST and transforming it and replacing different parts work on this as well. So this makes it very easy to extend. It's very accessible for any other person to add their own transformations and to make bigger and better kernels automatically generated. So then there's the transformations in the middle, and as I said, these are very much very standard. So for example, some of the easier ones, if there's not a where clause, we desugar that to a where clause that's always true. Because in hardware you will always need some value, right? And same thing with some of the constant propagation on the bottom ones. Certain ones you can just remove, and that just makes your final code that you generate much easier to read. And then a look at the backend, which is what takes that Python AST and it generates your actual HLS C++. So it's an HPC-oriented transpiler, and it does all these languages sort of mostly any-to-any, although there's obviously some caveats with that. But so it uses Python ASTs to do basically cross-compiling from one to the other. And this project only really uses the C++ unparser from this project, because obviously the source of this compiler is SQL, and it was not supported, so we hook in halfway through this and then just let it generate the actual C++. And so the integration with Fletcher, this is a part of the Fletcher project for Vivado HLS integration in this case. And so what it does, it represents most of the arrow types as normal C types. So these are just structures, and you can use these in C like you would use most of your primitives in C, because most of the operators are fully overloaded, so it will handle all the auxiliary signals that Fletcher needs for its streams. You can just do A plus B, and it will handle all the extra flags that need to be passed along to your results. So you don't have to manually, handle the data, handle this signal, handle that signal, and so on. So then, obviously we needed to test this. It needs to have some target to verify against. So I used MySQL, but I could have picked any other SQL implementation. This is just for logical correctness checking. So first tested it all in software, and then we moved on to hardware, and we've finished with actual in-cloud hardware testing. And so there's different stages to testing, and they all need the output exact same. So obviously the easiest one is to just run the SQL query on a known SQL server, and then just store the output so you compare it to your other things. Then for ease of development, just run the actual HLS code like it's normal C, so run it through GCC and run the code. This obviously it's very easy to check if this is correct. And this is also one of the advantages of using HLS, is that your testing, your first functional testing, is actually very straightforward, because it's just, a bunch of C++ code. Then you can actually run it to Vivado HLS or your other HLS tool of choice, and it has very nice code simulation features, so it runs the actual kernel in hardware, and your test bench can still be the same as essentially your code for your C++ testing, because it can still be in C++. So this is just a software and hardware code simulation. And then when all that works, you can use the Snap framework from OpenPOWER to actually run it on FPGAs. And the compiler generates the projects for you. It generates most of the other helper files. So when you run the command, it outputs your project for you, and you just hit, make image, and it will create the image for you, and you can just run it on the FPGA. And so obviously one of the use cases could be to run this in a just-in-time fashion in certain big data frameworks, for example. And so the hardware tests were run on Nimbix on one of their power nodes with the 250S FPGA cards. This is a Kintex part. And so I have some actual throughput numbers. So these are potential throughput numbers running on the highest Fmax that, in this case, Vivado would let the part run. So this is per instance. And these instances are fairly small. And this is, so you can have multiple, so you could easily saturate your system bandwidth. And these are all using only primitives. So the problem becomes when you read in strings. Right now the implementation is a little bit naive, so it reads in strings 1 byte at a time. As you can see, obviously the bandwidth is not that staggering. Still, these are very small, so you can probably put hundreds of these on an FPGA or more with room to spare. So these are the ones from simulation, the numbers, and then the actual hardware runs. It's supposed to be 1,000, and the hardware run was about 950. So these numbers, they match reality. And this is over just one simple 32-bit integer load-in. So that's about 30 megabytes per second per bus bit. And because it's an FPGA, this scales very well by just making your bus wider, having more columns. The more columns you have, the higher your throughput gets. And otherwise, you'll have to parallelize them per record batch. So you can obviously just run multiple instances and each give them a little bit of data to filter, and they will just filter, push it out to whatever is afterwards, and so on. And so here's some of the post-implementation results of, if you would run them on Nimbix, it's the far right column. Right now, those FPGAs run at 250 megahertz. And so this is per instance what you would get out of most of these. And then here's the resource usage. So as you can see, all of these are very, very small. All of these numbers on this target part are less than 0.5% of the FPGA. This is without the actual interconnect. This is just a filter core. This is just to give you an idea of how small these kernels are. Especially the BRAM usage is affected by how large you can have your strings, because it can do some, for example, string concatenation. It will need a little bit of BRAM. So obviously, if you scale up your string size, these go up. But this is for about 255 character strings. So it's fairly usable in a lot of applications that have smaller strings, for example. And then, as I said before, on the target part for this, if you ignore your interconnect costs, hundreds of these fit on a single FPGA. So your total bandwidth can be more than enough to saturate your CAPI 1 or 2 interface for some of these. And so there's definitely a lot of potential still here to make these faster, especially the ones that use strings. It's very naive right now, so if one would spend a little bit of time, there's a ton of potential to get maybe a 10x or a 100x, depending on how much effort you want to spend. There's some multiple elements per cycles functionality in Fletcher, the framework itself. And there's already some work done to get HLS to integrate properly with using multiple elements per cycle and presenting these to the user as essentially just little fixed size arrays. And obviously the code generation for this could make use of those same types. And if you go to 2 elements per cycle, because of the linearity of sort of how that load in and write out works, you get a latency that's half, and then you go to 4 and it's a fourth, and so on. And so if you go to a very wide data bus, you can easily gain 10x or even more on just simple string read in and read out. And then every advance in HLS, so if a full data flow gets enabled in, for example, Vivado HLS, this obviously gets you nicer pipelining, because right now the kernels, due to how Vivado HLS generates them, they can't really be pipelined. So they have to wait essentially until all the matching is done before they know if they can pass it to the output. So they do their matching on their input variables, and then they know, like, okay, this record matches the where clause, write it to the output. But if you can have more of a data flow sort of approach to how the HLS tool works, it can already start matching the next one while it's writing out sort of the previous one. This obviously gets you free performance by just having your HLS tool become better over time. And because it is written, sort of that intermediate is just C++, that just means it's very portable as well. And so then the end goal, I think, for me personally at least, what I would like to see from HLS is to start using HLS as an orchestrator more. So now you put HLS kernels into HDL, but obviously it would be very nice if you could use HLS to even easier, essentially, to instantiate maybe hundreds of these sort of semi-automatically from HLS. This would lower that bar to use FPGA accelerators in big data, for example, even more, which I think is important just to get sort of FPGAs used more. And then in the far future, hopefully HDL gets relegated to what assembly today is for software. So you'll end up writing most of your stuff in some higher level, and then you write your performance critical code in HDL. And thank you very much for your time. That was it.
So it seems like the work is maybe a compiler to translate SQL language to HLS.
Yes.
So does that mean that if I want to use a new SQL statement, then you need to review the whole hardware image?
Yes, that's correct.
Okay. And is there any, is your work connected with any real database? Because it seems like the whole work is based on Fletcher.
Yes,
so
correct. So
it seems like you are only process the one data format. So you don't care about the upper level databases.
No, so it's not necessarily like a database. It's where SQL was just chosen as sort of the representation of the filters because most people are familiar with it. So it's a very easy and accessible sort of way to just write a filter as a SQL query that's sort of intuitive. It could be, you could make any front end for this, so any filter, the specification could work.
So is the compiler open source?
Yes, it is. The bottom link is it's Apache 2.0, so the code is fully open. It's the bottom one here.
Okay, well, good.